Wells are the one place that people tend to interact with groundwater. So a well is just a hole that's drilled into rock or sediment down to a depth below the water table for the purpose of extracting groundwater. Overuse of groundwater causes lots and lots of problems, though, and we can see that in these wells. So here's an example of where you have wells dug into the water table, and these wells are obviously um, down below the bottom of the well is at least below the water table, so those are producing wells. In this case, you can see there's a field that doesn't appear to be using any of that water. So I said overuse is a big problem. And one of the first signs of overuse of groundwater is what's called the cone of depression. That's called a cone of depression because if you think about what this shape looks like in 3 dimension, it actually makes a cone shape. So this is a localized lowering of the groundwater table. And what happens is, if you pump water out of a well, that water in the groundwater table permeates through and it fills in that area where you remove the water. But if you're taking out water faster than the water can move back in thanks to the permeability, then you get one of these, a cone of depression. You can see, in this case, that was enough to cause this well to go dry. And here's a quick little cartoon of this happening too. You can see the waters are pumping from the well, but the well on the right is using a considerably larger amount of water, and you get a cone of depression where that water table is dropping and dropping, and now the well has gone dry. So what are the implications of overuse of groundwater? Well, let's go back and look at the Ogallala Aquifer again. And you can see this is a map of water level change. So this is how the water table has changed over time. And you can see there's regions without much of a change, and those are those big white regions. But the regions, particularly throughout the panhandle of Texas, where the water table has dropped over 150 feet, and that's pretty significant there. In some places, this is a much more acute problem, like in California, with particularly in light of recent drought systems. So the picture on the left is one of the most famous groundwater pictures ever taken. So this man is standing in the San Joaquin Valley of California. So this part of California is Central Valley. It's down in the southern part of it. This is a major agricultural area. Something like a third of the vegetables in the United States are grown here. Except if you've ever driven through this part of the country, you'll know it's really, really dry. And that's like Bakersfield up to Fresno. And actually, Mendota, where this picture is taken, is just west of Fresno in the valley. And so what this sign shows you is where he's standing at the very bottom of this pole is a sign that says 1977. And what that means is that was where his feet were in 1977. So that's the level of the ground surface. Makes sense. That's where he's standing. If you look at the sign about halfway up, this is 1955. 22 years earlier, this is where his feet would have been. Way up here by the sign. And even more incredibly, at the very top of the picture where it says 1925, that's where he would have been standing 52 years before. That's a significant change, but an elevation between those. So this is a problem called subsidence. And subsidence is caused because of drawdown of the water table. This causes the sediment to collapse and compact, so all the sand and gravel collapses down. And this in turn makes the land surface above that drop down in this process called subsidence. So the San Joaquin Valley of California has experienced severe historic subsidence. And they recognized the problem in the 70s and took some pretty significant steps to combat that. And that's what this map shows is from 1926 to 1970. You can see there's locations here where particularly Mendota, which is right in this area, the most severe area here, there were places that dropped over 8.5 meters. And that's a big deal. That is enough to break power lines, to break phone cables, to break water lines, to break sewer lines. And really mess up a lot of other infrastructure as well as homes too, because foundation of homes can't handle the ground dropping quite like this either. But unfortunately, thanks to the drought that's happened recently in California, it started back happening again because there wasn't enough water coming from the mountains where they usually get their water from. They usually get their water from the Sierra Nevada, and they rely on snowmelt coming off of the mountains. But because of the drought, they weren't getting enough snow, which means they weren't getting any water off of it. So they turned back to using groundwater in these locations. And so you can see here is that area again. So there's Fresno, and Mendota is right over here. And just north of there, over the course of a couple of years, the whole area dropped by 540 millimeters. Now, millimeters we usually measure pretty small, but that's 50 something centimeters. That's a pretty good drop in just 2 years. And so what they found is that all the subsidence in this area really started happening again because of the drought. The good news is they're not using as much groundwater right now because the conditions are a little bit better, but it's still an ongoing problem. California is not the only place that has subsidence. The whole United States is covered by areas. Something like 17,000 square miles are actually affected by subsidence. And so you can see the valley in California stands out pretty well, but look at southern Arizona. We're going to look at southern Arizona's subsidence problems, but also there's the Ogallala Aquifer. So that overuse of that aquifer is causing subsidence there. And a couple of things that happens is as that water is extracted and your sediment collapses, it reduces the porosity. And you can't get that back. Once it's collapsed, that's all you're ever going to have. So there's pretty important implications for long-term groundwater storage, because even if they stop using groundwater completely and let it refill, you're never going to get as much water as you had. So let's take a little bit closer look at Arizona. In Arizona, we have what's called earth fissures, and these are a direct result of subsidence due to groundwater withdrawal. So an earth fissure is a crack on the valley floor due to subsidence caused by groundwater withdrawal. So these are pretty nasty. They're not super dangerous. The only known death from one of these was a horse that fell into one out in Queen Creek, I believe, a couple of years ago during a monsoon storm. Now, these can vary a lot. The size of these cracks in the picture on the left, you can see there's a really small crack. You might not even notice it. And then there's a guy standing in the middle of that crack on the right. It looks a whole lot bigger in this case. Here's another look. This is southwest of Picacho Peak. It actually got a lot of attention because somebody flew a drone over it and got some pretty good footage of this one. And this was opening up fairly newly when they did that. And you can see the scale of this thanks to the people standing there. The longest one in Arizona is something like 10 miles long, which is enormous. The Arizona Geologic Survey was tasked by the state legislature to map where these happen, not to fix it, but just to know where all of these are. And so the map on the left is Maricopa County, so the Phoenix areas. And you can see there's quite a bit in the West Valley out there by Luke Air Force Base. There's a bunch out the Harquahala Plain. The largest one in Maricopa County is out here in Harquahala. There are some down here in Pinal County, just west of the town of Maricopa. There's a bunch down in Queen Creek. There's quite a bit out in Apache Junction and far east Mesa, plus Scottsdale and Paradise Valley. And then some pretty significant ones are down south of here too. Right around Casa Grande, Eloy, and Picacho. There's actually one really long one that crosses the interstate in Picacho. And what I want to show you here, this is a picture from Apache Junction. This is right off of Google Earth. This is the intersection of Ironwood and Baseline roads. And out here, there is kind of a mixed use. You can see there's a big housing development on the left or the west side of the image here. And right in the center of the image is a really industrial area. There's some kind of factories, there's warehouses and all sorts of stuff there. And you can see some natural drainage here. You can see little channels highlighted sort of by a plant that drain mainly to the southwest part of the map. But then there's some kind of strange things happening, like this line right through here. This is actually a giant crack in the earth. That's an earth fissure. It continues on down through here. There's more under there. There's another one. Here's another really big one just south of Guadalupe Road too. And what I'm going to do is I'm going to lay a map that has them all marked. So all of these lines that you see on the screen are locations of big cracks in the ground. And you can see that one that shows up really nicely. The one that shows up really nicely starts at it's right between baseline and the 60, crosses baseline, crosses this empty field, crosses this road. What's cool is the last time I was out there, and that's been within the last probably 4 to 6 months, this road right here, Houston Avenue, is actually shut down because the fissure's opening under it and the road's collapsing in. So it crosses under there. It actually goes under a bunch of buildings right here too. So there are buildings that are literally built right on top of these giant cracks. The ones that are sort of unfortunate are these over here because this one goes right up to the back of that housing development. Now it stops, at least on the map, right at the housing development, but that's only because the people mapping couldn't see them because these houses are here. The back wall of some of these houses have cracks up running through the back cinder block wall. So we know these are underlying those houses. They're not just there. And I mean, a crack might seem like not much of a big deal. But when it crosses beneath a house, that can cause some pretty significant foundation problems because these cracks aren't just a surface problem. The crack actually goes all the way down to the water table, and in some of these cases out here in particularly this area, the water table can be 100, 200, 300 feet deep. So that crack goes all the way down, which is pretty gnarly. I think these are really interesting. Now locations of these are directly related to where we have the most groundwater use. So Ogallala Plain, lots of groundwater. So this is a water table drop up to 1980. So this is actually pretty old data. But in the Ogallala, out in West Phoenix, down in Chandler Heights, down in Picacho, these are areas where the water table is dropped by over 400 feet. These are all very agricultural areas, even now. If we were to look at Google Earth in the Picacho area, farmland as far as you can see, and it's all heavily irrigated. And it's because there's subsidence in those areas, because when the groundwater drops, or the groundwater table drops, that sediment collapses and then the surface goes with it. So here is some subsidence from the Phoenix Valley. So if we look out here in Mesa, since MCC is right here in Mesa, Mesa's actually had some pretty significant drops of like 5 millimeters per year, historically speaking. And that's pretty significant there. And so what you're going to notice is the fissures aren't happening in the middle where the subsidence is happening. The fissures are actually going to happen on the edges. And there's a very good reason for that. We're going to look at that in just a second. Here's another area of subsidence. It's a little bit different way of looking at it. This is out in Glendale, Peoria. So this is where the 60 or Grand Avenue goes out. So if you know, like the World Wildlife Zoo, it's actually very, very close to these areas out here where this is happening. Because it is right on the corner of like Olive Avenue and the 101. So it's right on the edge of the main part of the subsidence here. But from May 1995 to February 1998, so less than 3 years, that area highlighted right here in the middle by the interference pattern actually subsided by 20 centimeters, which is a lot. So the subsidence in and of itself is actually pretty dangerous because, like I said earlier, you get a lot of infrastructure damage. It also increases flooding because now those are areas that are lower in elevation, so water is going to tend to pool there. But the fissures come along with this. So the fissures are because of subsidence, but they don't happen in the middle of the subsidence area. It happens along the edges. And that comes down to particularly southern Arizona's structural history. So in the structural history, the subsidence is going to occur within the basins of the basin and range region. So you have basin and range, right? You got normal faults. You got the grabens in the middle. The grabens are where our aquifers are located. They're filled up with a lot of sediment that's been eroded off the mountains. The ranges of the basin and range are the mountain systems. Those are the horsts that are left up high, or at least the tops of your half grabens. And those are often made of granites or metamorphic rocks, which are particularly impermeable, so you don't have any aquifers there. Right, so as long as your water table is nice and high and nice and healthy, the porosity is good, the water keeps those grains apart and keeps that porosity open. But once you start pumping that groundwater out, the middle of the basin is what's going to drop the most because that's where there's the most water and the most collapse happen. So the middle of the basins drop like we saw in the middle of Mesa or in the middle out near Luke Air Force Base. So the middle of the basins drops down, but the edges of them don't drop as much. And when they don't drop as much, you get cracks all along the edges of the basins right along sort of the foot of the mountains. And if we go back to where these things happen, what you're going to notice is most of these are going to kind of happen right along the base of mountains. These near Air Force Base are right on the edges of the White Tanks and the Harquahalas. Hollows. They're right against these mountains. Down in Queen Creek, they're butting up against the Santans. On AJ and Mesa, we're right on the edge of the McDowell Mountains and the Superstitions. Scottsdale, these are the foothills. In PV, it is along the edges of the Phoenix Mountains. Out here in the Picacho Basin in particular, this really long one, you can actually see this from the interstate if you're looking in the right place. This is the first one ever identified in Arizona that started back in the 40s, which was a big boom in agriculture in Arizona, so it makes sense. That runs literally right along the edge of the Picacho Mountains. And so if you think about it too, these are all areas that saw a lot of population growth, particularly during the big housing boom that got wrapped up, about 10 years now, 10 years ago. So these are, and even now, these are kind of the fastest growing areas of the valley still. And so there are houses being built right on top of all of these big cracks. And you can fill them in and put a house on top of them, but one good monsoon storm to help sort of erode some of that fill material away, and it becomes a lot bigger problem. Another kind of interesting hazard that comes along with groundwater is karst. Now, karst is a landscape that's created by groundwater dissolving rocks such as limestone, gypsum, marble, sometimes even halite. And so this creates a karst landscape. This is what you see right now. But you can recognize this most easily by the presence of caverns, which are just big cave systems. Everybody kind of knows and loves these. Even Arizona has a number of them. Our big caverns here in Arizona are Karstner. And if you haven't been down to southern Arizona and got to go to Karstner Caverns, I highly, highly suggest it. The caves weren't discovered till the 70s. The people that owned the land didn't even know about them until like the 80s. And then they worked together with the discoverers to turn that land over to the state of Arizona and made it into a state park in the 90s. And so these caves haven't had a lot of the destruction that other caves have, which are really cool. It's also an important area for bats. There are bats that are living down in here, which are kind of fun. All right, so we get speleothems inside these caverns. Um, those are a sedimentary process where travertine is actually deposited after limestone is dissolved away. And we talked about this process some when we did sedimentary rocks. But they're on the ground. Those formations that form when the water's dripping down, those are stalagmites because they might reach it all the way to the ceiling. The stuff hanging from the ceiling are called stalactites because they hold tightly to the ceiling. And sometimes you get lucky and those two grow together and you get column. Now, there's all sorts of other weird speleothems, and I always say that cavers are hungry people because you get cave bacon, cave popcorn, there's cave eggs, but then you've got drape soaps and soda straws and all sorts of beautiful things that you have to go see to believe. Now, every once in a while, your cavern gets so big and so much of the limestone is dissolved out that the ceiling gets really, really thin and the ceiling collapses in, and that forms a sinkhole, which is one of the other really easy ways to recognize a karst area. These are both shots from Florida. I really like the one on the right because that one particular house did something terribly, terribly wrong to be right in the middle of that bullseye of that sinkhole. Arizona's got sinkholes too. This is Montezuma's well. So this is a sinkhole up in the Verde Valley. If you're ever on your way to or from Flagstaff and the traffic on the 17 is getting nasty, you should stop in here and enjoy it for a little bit. It's one of the few places that we have standing water year round in Arizona. Remember when we talked about groundwater table and it making natural lakes? I don't think this is considered a natural lake, but it is natural water that's always there, which is pretty cool. And so if your sinkhole is shallow enough or deep enough and your water table is close enough to the surface, sometimes these fill up with water. And so the water at the bottom of the sinkholes make this lovely big round lake. If you remember all the lakes in Florida, super round, those are all sinkholes. And sinkholes tend to be deadly in Florida because they happen so quickly. And so that is one of your famous ones, at least for Arizona, is Montezuma as well. We keep on rocking. Here's a really neat one that formed in Guatemala back in the early 2000s, I think. This might have been the 2005 one. So this sinkhole, you can see it actually collapsed under an apartment building, and the apartment building's completely gone. And the first time I saw this, I was convinced it had to be photoshopped because that hole is so dark. And the reason why it's so dark is it is that deep. This sinkhole is actually over 330 feet deep, which is enormous. You can sink the entire Statue of Liberty in. And then put another one right on top of it, and you'd still not see the flames sticking out the top. And what's crazy about this is if you look at this area now, it's road and rebuilt. They just stabilized it, filled it in, and stuck some buildings back on top of it, which is pretty scary. Now, tower karst is the end process of this karsting and dissolving. So what happened here is these are blocks of limestone. This used to be one big layer of limestone, but everything around it has been dissolved away so far. One more hazard really quick for you is contamination. So this diagram shows you some really common sources of contamination for groundwater. And that includes farm sewage, landfills, waste containers, injection wells. There's companies that have water that they inject polluted water into the ground just to get rid of it. There are leaky gasoline tanks, and those leaky tanks are a big problem in northern Arizona. If you've seen the movie Cars, right? In Radiator Springs, you saw they had footage from back in the day when there were all sorts of people coming through, and there were lots and lots and lots of cars coming through. And then now everything's shut down because nobody's driving through on Route 66 anymore. Well, that is basically the history of northern Arizona. So there are towns in northern Arizona that were huge, bustling areas when Route 66 was active, but when they rerouted the freeway and put the I-40 away from that old Route 66, they didn't need those gas stations anymore, so there's lots and lots of leaky tanks under there. Other problems are fertilizer for crops and septic tanks. Now, septic tanks tend to be pretty gross in and of themselves. So a septic tank is just um, if you don't if you aren't hooked up to the water sewer system, if you flush your toilet, all that water's got to go somewhere. And so if you're not hooked up to the city sewer, that water goes to a septic tank, and it's a big box that's buried in your backyard. It's got enzymes in it to break down the waste material that you're flushing. And then all the water drains out of it. But septic tanks tend to leak and they have problems. And so what happens is that waste, well, that's a nice way of saying poop, right? All that poop water starts leaking out of your septic tank. And in some cases, it causes contamination of nearby wells. And this is what's happening here, is you have tilted layers with an impermeable layer that acts as a barrier, and that contaminated water is just being funneled right into their next door neighbor's water well that they use for drinking. The good news is that aquifer systems actually tend to work as a pretty good filter for groundwater. So a lot of times even contaminated water that's carried through the aquifers can become fairly clean over time because of that natural filtering action. And that's what's happening in this picture here is the septic tank is leaking out, but the most of the contaminants are being filtered before it gets to the drinking water for the next door neighbor. But let's look at this house a little bit closer. So this house has a leaky septic tank, and they have a small well that's giving them clean water because they are up the water table from the septic tank. And that means as long as the water table is higher over here on the right, the water's flowing to the left of the screen, and that's carrying that waste along with it. So that's good for this guy. But you notice he's got a lot of kind of empty land out next to him. Maybe he decides he wants to grow some sort of cash crop. And he's going to plant that field, and he's going to put a big well that he's using a lot of water from to irrigate those crops. That heavily pumped well is going to cause drawdown on the groundwater table, and it's going to form a cone of depression, which changes the hydraulic gradient. And when you change the hydraulic gradient, you change the direction of water flow. And what's happened now is that instead of flowing away from his well, that septic tank is draining directly into his well. That's what they're using for drinking, for cooking, for bathing, for cleaning. And that is not a good thing.